Alrighty, hey AP Chemists, this is going to be the important information part 2-2. We're going to be looking at atomic structure. So in this video, I'm going to be discussing things like what the atom is made of. I'm going to start with the electron, and then we'll talk about the nucleus of an atom, and then we'll get into protons and neutrons. You may or may have heard these before, but if not, this will be a nice little review here. So the first subatomic particle, things within a particle within the atom that was discovered was the electron. There's all this fun information here. This is just fun facts. You're not really going to need it for the AP exam. Fun facts. This is fun facts. You're not going to be asked about Millikan's oil drop experiment or J.J. Thomson's cathode ray tube, although I have seen questions about like who J.J. Thomson is. He's the one who really uncovered and discovered that there was a negatively charged particle in the atom, and we called it an electron, and it was in a sea of positive charge. And so I'm going to jump on down to here. That atom was called the Plum pudding model by J.J. Thomson. And so earlier models had Dalton's model. Remember I had the law of atomic theory? This is the earliest model where it was literally just a sphere, nothing, no charge, nothing. And then J.J. Thomson was like, it's attracted to some things. There's got to be some sort of negatively charged particle because when I put it in a cathode ray tube, it gets deflected towards the positive plate. So it must be attracted to positive, therefore it must be negative. And so I'm going to kind of redraw the plum pudding model a little bit more plum pudding-y. Sometimes they call it the chocolate chip cookie model. Basically, it would be like these negative chunks in a positive sphere. So negative electrons in a positive sphere. And that would be the plum pudding model. Then years later, with Ernest Rutherford's discovery on radioactivity, he did this gold foil experiment in which he shot alpha particles, which are positively charged particles, at gold foil. And he noticed that most of the alpha particles would go through unaffected, meaning that there were mostly empty space in the atom, mostly empty space. But then some were deflected, hitting something positive. So some went through, some did not. And so what did this interpretation mean? Most alpha particles passed through unaffected. Most of the atom was empty space, like we said. Few alpha particles were deflected. Most of the mass and all of the charge of the atom is concentrated in a small, densely positive region called the nucleus. And later on, we'll find out that it contained protons. He did not discover protons. It's just, that's where they were. There are as many negatively charged particles as positively charged particles to make the atom electrically neutral. Very important information here. And so I love this little image and diagram here. These were the predicted results that if it was Thomson's model, the J.J. Thomson's model, all of the particles would go through. But the nuclear model, this is Rutherford, some of them went through, some of them did not. And so that means we had to turn our model from the plum pudding into something more of like a planetary model with the positive charge only in the center, and you have all this negative charge on the outside. So we call this the Rutherford model, sometimes referred to as the planetary model. Kind of like a planet orbits the sun. We have the electrons orbiting the nucleus, the positive nucleus. Then later, this was a successful model, but it was still incomplete, right? So we have electrons, we have a positive center nucleus with electrons on the outside, and hydrogen has 1 proton and helium has 2 protons, but hydrogen is 1/4 the mass of helium. There must be another massive particle, and so subsequent experiments, especially by James Chadwick in 1932, figured out that there were protons that were positive and neutrons that were neutral. So now we have electrons, protons, and neutrons, where the protons and the neutrons were in the nucleus in the center, and the electrons were on the outside. So to summarize here, all atoms are composed of the same subatomic particles: protons, neutrons, and electrons. So protons, neutrons, and electrons. Protons and electrons have electrical charge, equal but opposite. Protons are positive, electrons are negative. These protons and electrons exist in equal amounts, making the atom neutral. So if I was carbon, I would have 6 protons and 6 electrons, and I would be neutral. Hydrogen would have 1 proton, 1 electron, and it would be neutral. And then there are neutrons that have no charge. This table is very important because I want to point out and kind of highlight in a different color. Here's the relative masses of protons and neutrons, and then here's the relative mass of an electron. Look at how small that mass is compared to protons and neutrons. Protons and neutrons are about 1. Look at the electron, about 0.0005. It is 1,800 times smaller. The electron is 1,800 times smaller than the proton and neutron. Electrons are relatively massless. We don't really consider electrons to have mass or add or take away mass from the atom. And so the way to think about it is like if you're a millionaire and you have $1 million, like a proton, and you lose a penny, that penny is like losing an electron. You're still going to be a millionaire. You'll have 999,999.99 cents. But you'll still basically be a millionaire, technically. The pennies are kind of like the electrons here. They really don't have too much worth. But electrons are negatively charged. Protons are positively charged. Neutrons are neutral. They don't have a charge. And so elements are typically defined by their number of protons. So every element consists of protons, neutrons, electrons. The number of these particles identify them. So the number of protons defines the element. So, for example, 2 protons belong to helium. If I had 8 protons, that would mean Z, which is the atomic number, would be 8, and that is oxygen. And we'll talk more about this in the next lecture. Each element is identified by its own unique atomic number, which we call Z, and that's represented by the unique number of protons. Electrons and neutrons can change. Electrons and neutrons can be different for an element, for any given element. Protons do not. Protons need to be constant. Protons are constant for a given element. So just writing an important little note here at the bottom of the page. I know it's going into the next one, but you could write that all there. So for example, anything that's oxygen must have 8 protons. Maybe it could have 6 electrons, and that's later. Maybe it could have 9 neutrons, and that's later. But anything that is oxygen must have 8 protons. Anything that's carbon must have 6 protons. Anything that's hydrogen must have 1 proton. Electrons and neutrons can change. And that is it for this lecture. So use this information about electrons, protons, and neutrons now and answer exercise questions 2 and 3. Exercise 2 asks you about the statements that are consistent or not. And then exercise 3 wants you to circle all that are true about subatomic particles. Any questions or concerns, please let me know.